Hello everyone, welcome back to our course on abstract algebra. Today I want to take a break and step back and review everything we have done so far by discussing one example of a group that I haven't talked about, which is a very important group in group theory and in other areas, which is the Quaternions, Hamilton's Quaternions. There is a plaque in Dublin that says, "Here, as he walked by on the 16th of October, 1843, Sir William Hamilton, in a flash of genius, discovered the fundamental formula for the quaternion multiplication," and it describes how the quaternions work. So let me show you then what is the quaternions. So here is how we define Hamilton's quaternions in group theory. So let G be, actually I'm just going to call it as we usually call it, Q8. Q8 is going to be a group with 8 elements that we're going to call 1, I, j, k, and then their negatives, with the relationships that I squared is the same as j squared is k squared equals minus 1. And then I'm going to write them all out. We have that I times j equals k, that j times k equals I, that k times I equals j. You can remember this if you write I, j, and k. If we go in this direction, then we get the next one. So if I multiply I times j, I times j, I should get k. J times k, I should get I, etc. And if I go in the other direction, then I get that other letter, but with a negative sign. So j times I is minus k times j is minus I, and I times k is minus j. That is too many relations. One can express this more briefly, but those are all the relations that one needs to know. So if I go in that direction, in the red direction, I get the next letter, but with a negative sign. Okay, so this is how the quaternions are defined. Then Q8 under multiplication is called Hamilton's quaternions. Or simply the quaternion group. And let's do some group theory with this example in mind and just review everything we have seen so far, which is, for example, the very first question is Q8 under this multiplication a group? So we have to show the axioms. The very first thing to check is, which I've called sometimes the zeroth axiom, is that Q8 under this multiplication is closed. And it is closed just because of the definition of Q8 in the parentheses. We have every single possibility of a quaternion. The multiplication of those is defined by the definition. So I times j is k, etc. It gives you the closure. It tells you how to multiply any two elements in that group. The signs plus or minus 1 act like you would imagine. Minus 1 times I is minus I, etc. And all the other multiplications of I, j's, and k's are defined and described by those elements, by those relations that are described in here. So it is closed in the multiplication. For the associativity, the fact that it's associative, so now is Q8 under multiplication associative, one can do the same and just check what happens if I do I times j times k, and if I write it first as j times k, then we know I times j times k is in the right order, so that will give me I, and I times I is minus 1. What happens if I do I times j times k? Then I get I times j is k, and times k will also give me minus 1 because I is square and k square is minus 1. So this is just one example, and you could try to do all the possibilities of ij's and k's and check that a, b, c is a, b times c, and also a times b times c. But let me give you actually more information about the quaternions, which is very useful to prove associativity in one shot. So it turns out that the quaternions can be represented as matrices. So there is another representation of Q8 as a group of matrices, of 2 by 2 matrices, in fact, given by these matrices. I'm going to call these matrix I, this matrix J, and this matrix K. And then this is the subgroup generated by these matrices inside GL2 under the complex numbers. And then one can check, and maybe I'll leave that as an exercise, that you can check that this group, so the identity I, J, K, generate a group such that I times J equals K, and J times K equals I, and J times I equals minus K, etc. So it behaves just like Q8. When we say it behaves just like Q8, soon we will define the concept of isomorphism, and then we'll see that this group is isomorphic to Q8. But on the other hand, this group, if I call this G, let's call it G8 for the matrices. So G8 is a group, and the multiplication is associative in particular, because matrix multiplication is associative. So one can check that Q8, the multiplication there, is associative just because there is a form of the quaternions in terms of matrices that give me that the multiplication has to be associative because matrix multiplication is associative. Let's keep going, just checking the axioms. So it is associative. What about, is there a 1 in Q8? Is there a multiplicative identity? And yes, actually, 1 is one of the elements of Q8, which is generated by minus 1 and I and J and K. 1 is one of the elements that appears in there in our list of defining elements of Q8 from the original list. Here is 1, and 1 works as the multiplicative identity because 1 times I is I, 1 times J is J, 1 times K is K, 1 times minus 1 is minus 1, etc. So it works for every single element. 1 behaves as the identity. In fact, I could have written 1 times any plus or minus I is plus or minus I, 1 times plus or minus J is plus or minus J, 1 times plus or minus K is plus or minus K, and 1 times plus or minus 1 is plus or minus 1. So 1 is the neutral element with respect to multiplication. What else do we need? We need inverses. Are there inverses? And also, there are inverses. The inverse or plus or minus 1 is just plus or minus 1. 1 times 1 is 1. Minus 1 times minus 1 is 1. And then, what is the inverse of I? For example, what is the inverse of I? Well, that will be minus I, because I times minus I will be minus I squared. I squared is minus 1, and this will give me 1. So what happens is that the inverse of plus or minus I is minus plus I. The inverse of plus or minus k is minus plus k, and the inverse of plus or minus j is minus plus j. So every element has a multiplicative inverse. So that checks all the axioms, and that implies that Q8 under multiplication is a group. Okay. What other things have we learned about? We've learned about the order of groups. What is the order of Q8, which is the number of elements? We know that Q8 is plus or minus 1, plus or minus I, plus or minus j, plus or minus k. So there are precisely 8 elements. This will come in handy when we do examples with Q8 about Lagrange's theorem. So we see that the size of subgroups divides the order of the group. Okay. We have also learned that there is a special type of group, which is the abelian groups. So is Q8 abelian? Oh, by the way, this 8 is 2 to the 3. And so this Q8 will be an example of what we call a 2 group. Because this is a prime power, then we say that Q8 is a 2 group. And more generally, if a size of a group is a power of 1 prime, we say G is a P group. And those are important groups in group theory. So this is an example of what we call a 2 group, and it's a non-abelian 2 group. Q8 is non-abelian. It's non-abelian. It's not commutative, because if I do I times j, I know I get k. But if I do j times I know I get minus k. Again, remember the triangle of elements, that if I go in this direction, I times j, I will get k. But if I go j times I, then I will get minus k. By the way the multiplication is defined in Q8. So since k is not minus k in Q8, Q8 is not abelian. Okay. What else have we learned? We've learned about orders of elements. So let me write about that. So how about what are the orders? What are the orders of each element of Q8? Well, I can just start by listing elements. The order of 1, I don't need to square 1, 1 to the 1 is 1, so the order of 1 is 1. The order of the identity is always 1. Minus 1 is not 1, but its square is 1, so the order of minus 1 is 2. What about I? We have I squared is I squared is minus 1 times I is minus I, and times I is 1. So that tells me that the order of I is 4. And similarly, the order of j, the order of k, it is also 4. What happens with minus I, for example? Minus I is squared will be I squared, which is minus 1. Then times minus I get I, and I times minus I get 1. So the order of minus I is also 4, the order of minus j is also 4, and the order of minus k is also 4. And remember that we have seen as a corollary now of Lagrange's theorem, we have seen that the order of every element divides the order of the group. And in this case, Q8 is 8, and the order of every element, the possibilities we have seen are 1, 2, or 4, are divisors of 8. So we have seen that it does work, that every order is a divisor of the order of the group. Okay, let's write next. Write a Cayley table for Q8 under multiplication. What that means, remember, a Cayley table is a table of multiplication of elements by elements. In principle, I would have to write a table in Q8 and their multiplication of every single element. There's 1 and minus 1 and I and minus I, etc. I'm not going to write the minus signs because how minus 1 operates is very easy. So let me do an abbreviated table of Q8 under multiplication, but I'm just going to write how I, j, and k behave essentially, instead of writing every possible multiplication out. When I multiply by 1, I get the same thing, and when I multiply by 1, I get the same thing on the left or the right. Now, each entry in here is going to be the top by the top row by the column. So each one of those entries are going to be, so for example here, let me write, here is going to be I times I, but here is going to be j times I. So the number in the column by the number in the row. Actually, let's do row by columns. I think that's more natural. So let me do that is going to be I times j, row by column, sure. So I times I is minus 1, j times j is minus 1, and k times k is minus 1, so there are going to be minus 1s in the diagonal. I times j, that I know is k, and I times k, I'm going to need my cheat sheet. What happens if I do I times k? I'm going backwards, so I have to get minus j. J times I, I'm going backwards, so I get minus k. J times k, that I'm going forward, I get I. K times I, that I'm going forward, so I get j, but k times j, I'm going backwards, and I get minus I. So this is how the multiplication works, at least for the positive 1i, j, and k. This is a Cayley table, or a partial table, I guess, but that is how it works. Okay. So just write the dot here like that. Okay, so that's how a Cayley table works. You could do a complete table or this sort of like abbreviated table because we know how minus 1 works. Let me ask a new question. So how about write all the elements in the subgroup generated by I. Remember that a subgroup generated by one element will be, well, the identity, and then I, and I squared, and I cubed, etc. And we already know how I works. The identity here is 1, I, then I squared is minus 1. If I multiply by I get minus I, and if I multiply by I get minus 1, so I get 1. So that's all of it. So this is the subgroup, the cyclic subgroup generated by I is that one. Great. What else? Let's ask now then, well, what are all the cyclic subgroups? Right. All the cyclic subgroups of Q8. By the way, notice that the order is 4 of this subgroup, and 4 does divide 8, like Lagrange's theorem would predict. Okay. All the possible cyclic subgroups, well, I have one cyclic subgroup which is just generated by 1. I have a cyclic subgroup generated by minus 1 that will have 1 and minus 1. I have the cyclic subgroup generated by I, that is 1, I, minus 1, and minus I. And notice that if I did the powers of minus I also get the same thing. So this is the same as the subgroup generated by minus I. Then I have a cyclic subgroup generated by, say, k or minus k. If I generate by k, I get 1, k, minus 1, and minus k, which is the same as the subgroup generated by minus k. And finally, I have the subgroup generated by j and minus j, and that will have 1, j, minus 1, and minus j. Now, I have checked subgroups generated by one single element and any of the elements of Q8, so these are all of them. So there is 5 subgroups. There is 5 different cyclic subgroups of Q8. Okay. Now that I know what are the cyclic subgroups, I can ask, that was, I think, Q7, so let me ask another question, which is write all the subgroups of Q8. I don't think I need a question mark, just a dot. Write all the subgroups of Q8. So we do have already 5 of them. I have the subgroup generated by 1, by minus 1, by I, by j, and by k. That's 5 of them, and those are the cyclic ones. So I'm looking for subgroups that are not cyclic. So what kind of subgroups could I have? Well, now I have to have, these are generated by 2 elements, and I know what those elements are in there. I mean, these are all generated by 1 element, but in the subgroup generated by I, there is I and minus I, 1 and minus 1. So what if I have a subgroup that now has 2 different letters, an I and a J or a K, and so on. So suppose that I have a subgroup and there are 2 letters. For example, I and J are in H. Then what would happen is that, well, first of all, if I is in H, the subgroup generated by I also has to be in H. The subgroup generated by J has to be in H. And but then I do have I and J, so I also need to have that I times J, which is K, is in H. These ones tell me that minus 1 is also in H, and K is in H, and between all of this, I have that plus minus I, plus minus J, and plus minus K, and plus or minus 1. These are all in H, and therefore H is all of the quaternions. And similarly, you can show that if you have any of the 2 letters, you have the third. If you have 1 letter, you have also minus 1. So if you have any 2 letters that are distinct, then you have all of them. So it turns out that what we've actually shown is that the subgroups are. The only one that is not cyclic is all of Q8. The other ones are cyclic, so I have the subgroup generated by 1, so the trivial subgroup, and then the subgroup generated by -1, and then subgroup generated by I, by J, and by K. And that's all of them. So we have, let's see, all in all, I have 6 subgroups. And I actually have the orders is 8, 1. This has order 1, 2, 4, 4, and 4. And now you can see that the order of each subgroup, so if H is contained in the quaternions, then the subgroup order does divide the subgroup, the order of the group, which is Q8. Okay, so every possible order, which is 1, 2, 4, or 8, does divide the order of the group, which is 8, which is again a way to verify that Lagrange's theorem works in this case. I can also draw a diagram. We've done a lattice of subgroups in the past, so I can draw a diagram with all the subgroups. I have Q8, and I have the subgroup generated by 1, which is just here. And on top of that, there's a subgroup, which is the subgroup generated by -1, also cyclic. And then there is the subgroup generated by I, 1, -1, I, and -I. There is the subgroup generated by J, 1, -1, J, -J. And then there is the subgroup generated by K. I have 1 and -1 and K and -K. And all these subgroups contain 1 and -1, and they all contain the trivial group. And this is all of them. I have 1, 2, 3, 4, 5, and 6 subgroups. So that is the lattice of subgroups of Q8. Okay. One last problem, actually maybe more of a note. I wanted to show you, maybe just show as an example, not so much as a question, that remember we finished the last video about Lagrange's theorem. I showed you a formula that said if I have a group and I have a subgroup and a subgroup of that, and this is finite groups, then the index of K in G is the index of H in G times the index of H in K. And since here I have one chain of such subgroups, let me, so for example, let me show you an example in Q8. I have Q8, inside of Q8, I have plus minus 1 plus minus I, the subgroup generated by I. Oops. Let me just do a little bracket here. And inside that, I have the subgroup generated by -1. So this would be playing the role of H, and this is the role of K. So what is the index of plus or minus 1 in Q8? Well, that we know actually by Lagrange's theorem. This is the size of Q8 divided by the size of plus minus 1, which is 8 divided by 2, so it's 4. And on the other hand, I have what is the index of plus minus 1 plus minus I. This will be 8 divided by 4, which is a 2, times the index of plus minus 1 plus minus I, and this inside, which is a 2. So that 4 is 2 times 2, and this is a breakdown of those indices of subgroups inside the Q8 subgroup. Okay, the last note I wanted to relate also the quaternions to permutations. That was another big thing. We have seen in these few videos, these first few videos on abstract algebra. So it turns out that Q8 also has representation as permutations. Okay, so it turns out that I can do a subgroup of S8. Remember, these are permutations in 8 letters, in the numbers 1 through 8. And H is generated by alpha 1, 2, 4, 7, 3, 6, 8, 5. This is not obvious why you would pick these two things, but it turns out to work out. 2, 5, 7, 6. It turns out that these alpha and beta work like I and j. So it turns out that if I pick my k, in this case gamma, to be alpha times beta, then it's going to be, you can check that this is 1, 6, 4, 5, 2, 3, 7, 8. And you can check, and this is a good exercise, again, to double check that you know how permutations work. You can check that, well, that alpha to the 4 is beta to the 4 is the identity, that alpha beta is gamma, well, that's by definition, but that beta alpha is the inverse permutation of gamma, and so on, and all the other properties that you would check for the quaternions. So it turns out that H is, and we will formalize that as an isomorphism, is isomorphic to Q8. So we will formalize what this notion means. We're going to say that the subgroup of the permutation group S8 is actually isomorphic to Q8. Okay, so I think that sort of reviews everything we've seen so far, and next time we'll continue with isomorphisms, homomorphisms, and isomorphisms of groups.